Next, we'll have two adjacent spotlight sessions. Our moderator will be Yu Xiang from NVIDIA Research. I will hand it to you.
Next, we'll have two spotlight sessions. Each session has 4 papers, and I will first play the video of the 4 papers. Then we'll have a Q&A session for all the authors. Please submit questions from the Q&A button. I'll just play the first video on CMU.
Hi, I'm Thomas Wang, and I am presenting our work from CMU on cloth region segmentation for robust grasp selection. This is joint work with Aurora Qian, Brian Okorn, Lucien Zhang, and David Held. Cloth manipulation is a difficult task because the deformability of fabric complicates both perception and planning. While we could try to infer the full crumpled configuration of a cloth, it is difficult to do so from a single observation. We ask whether there is a simpler representation that is easier to learn and still allows us to perform a grasp suitable for smoothing and folding. We focus on the problem of grasping a cloth on its true edges and corners. We distinguish between true edges, as shown here, and apparent edges like folds and wrinkles, since grasping a true edge aids downstream folding tasks. The same applies to true corners versus apparent corners. Some previous work simplified the perception task using simulation or fiducial tags. Other work uses image processing techniques to model the cloth, which have difficulty distinguishing true edges and corners from folds. Other approaches integrate perception with interaction with the cloth, leading to perception runtimes in the tens of seconds. In contrast, our perception pipeline runs in a quarter of a second. Other papers do not explicitly reason about the grasp direction of the cloth. Our work shows that reasoning explicitly about grasp direction, as well as directional uncertainty, leads to large improvements in grasp success rate. We first train a network that takes a depth image as input and outputs a segmentation of true corners and edges. We obtain ground truth labels by painting a cloth and collecting images of it in various poses. Color is only used during training to obtain ground truth, and the network only sees depth images. The network is also trained to predict an inner edge mask, shown in green, which helps determine the direction of the cloth edge. Given this segmentation, our next task is to estimate a good grasp point and grasping orientation. To estimate the grasp direction, for every point on the outer edge mask, we find the nearest point in the inner edge mask. However, in complex folded configurations, there may be several nearby inner edges, which can lead to errors when grasping. To correct this, we evaluate the variation in grasp direction within a local neighborhood for every point on the outer edge mask. We then select the grasp whose neighborhood has minimum variation. Thus, we are choosing a point where we have low uncertainty about the grasp direction. In order to execute the grasp, we define a non-learned sliding grasp maneuver. Then we lift up the cloth and evaluate whether we have successfully grasped the edge or corner. Here you can see an example of our complete system. Our method observes a depth image of the crumpled cloth and segments it. It then estimates the grasp direction and directional uncertainty. Finally, we grasp a corner point or edge point with low directional uncertainty. As you can see, we are able to grasp the cloth corners or edges for many crumpled configurations. Of course, our method isn't perfect, and there are failure cases in which we grasp multiple layers of the cloth or fail to grasp. Our method can generalize to different cloth colors, sizes, and materials. The network takes depth as input, so it is invariant to color, and it is a fully convolutional network, so it generalizes to different cloth sizes. We evaluate against image processing baselines for edge and corner finding, and show that our method outperforms them in terms of both edge and corner grasping success rate. Here we show an ablation experiment demonstrating the large drop in performance if we remove our methods for both estimating grasp direction and grasp directional uncertainty, showing that both elements are key contributions of our approach. In summary, our method segments the true edges and corners of a cloth. It selects a grasp taking grasp direction and directional uncertainty into account. It grasps corners of cloths and edges from many complex crumpled configurations. We demonstrate that our method is robust to variations in cloth size and color. We'd like to thank our sponsors for funding this research. Thank you for watching, and please see our paper for full details.
So next paper is Action for Better Prediction on UPenn.
My name is Bernadette Bucher from the GRASP Lab at University of Pennsylvania, and I will present my joint work with Carl Schmeckpepper, Nikolai Matny, and Kostas Stanilidis, Action for Better Prediction. In this work, we present a model-based approach to incentivize exploration via an adversarial curiosity objective. Our method can mathematically integrate with many approaches to prediction and planning by choosing to take actions which minimize the score from a discriminator for trajectories formed from states, actions, and predicted future states. In our experiments, we integrate our method with a video prediction model and the cross-entropy method for planning, which form a commonly used pipeline for vision-based robotic control. This application highlights the increased computational efficiency of our curiosity approach, aiding its effectiveness in continuous high-dimensional settings on physical robot platforms. The pipeline in which we integrate our new discriminator method for curiosity is commonly known as planning from pixels. To accomplish manipulation tasks, goals are specified by human-designated start and goal pixels on an image. Then, the cross-entropy method is used to select actions to move from the start to goal state. The cross-entropy method samples actions from probability distributions approximated by how close the action will bring the robot to the goal state. The sampled actions are evaluated using a pre-trained video prediction model to determine which action selection results in a prediction closest to the goal image. As opposed to accomplishing a manipulation task, the goal of our variant to this pipeline is to sample the environment in order to find data which can be used to improve our prediction model. First, the video prediction model we use is pre-trained jointly with our discriminator. Then, the sampled actions are drawn from a probability distribution approximated by how unrealistic the resulting model predictions are, based on the discriminator scores. The sampled actions are evaluated using the discriminator, and the most unrealistic action sequence is taken. We hypothesized our curiosity method would yield performance gains in the inherent domain transfer task this robotic control pipeline faces by using publicly available datasets for pre-training the prediction models. In particular, the datasets available to pre-train the prediction models are not collected in the same lab environment under the same conditions, and not always even collected on the same robot platform as that of the target control experiments. However, using these datasets is important since requiring data to be collected from scratch on every target platform would be computationally intractable as a long-term solution. Currently, when leveraging these datasets, the prediction models are first trained offline on a dataset of robots taking random actions in a bin of objects. Next, a small collection of data is gathered of robots taking random actions in a bin of objects on the target platform. The data is used to fine-tune the pre-trained prediction model before the model is ultimately used to execute tasks. We propose an enhancement to this pipeline in which the samples used for fine-tuning the prediction model are collected via curious instead of random sampling. Specifically, in our experiments, the prediction model is pre-trained jointly with the discriminator on Sawyer robot videos in the publicly available RoboNet dataset. The discriminator is then used for action selection with the cross-entropy method to collect data on the target Baxter robot platform. This data is used to fine-tune the prediction model, which is then used to execute tasks. We present three main results regarding the performance of our method for this robot learning problem. First, curiosity increased object interaction in the data collected for fine-tuning. We measured object interaction by non-zero finger force records from Baxter's grippers, which indicate instances in which objects are grasped. Curiosity also increased exploration of the state space with more complex dynamics. In particular, the robot interaction data is collected in a bin of objects, and the contact dynamics of the objects with the edges of the bin is both complex and not modeled well by video prediction methods. More samples are collected in these areas of the state space with our curiosity approach, as measured by discretized visit counts. Finally, fine-tuning the prediction model with samples collected with our curious policy resulted in statistically significant improvement in prediction error of the model during control task execution. We plot the prediction error improvement with different quantities of samples used in fine-tuning, and find the improvement is most pronounced when lower numbers of samples are used to fine-tune. In future work, we plan to include task completion results for our robotic experiments. We also plan to evaluate our method against other curiosity approaches in a less complex experimental setup, since existing curiosity methods are not computationally tractable for this robotic control pipeline. Thank you very much for your time and attention, and we look forward to any comments or questions.
The third talk is learning video server policies while planning cloning.
Hello and welcome to my presentation, and thank you for your interest. I'm Ulrich Vieck, and my collaborators are Robert Platt at Northeastern University and Kate Sanko at Boston University. I'm presenting our work, Learning Visual Servo Policies via Planner Cloning. Our problem setting is to learn a pixel-to-torque controller for manipulation. We want to learn a control policy for achieving a desired hand pose with respect to novel objects in the environment. We focus on the free space motion without contact. Examples are policies for mating a cap on a bottle or inserting a peg into a hole. How can we learn such a control policy? Deep reinforcement learning is less sample efficient and slower to train than supervised learning due to sparse and high variance rewards. The idea is to use behavior cloning, a form of supervised learning. We estimate the Q values using a full state motion planner in simulation, clone the Q values to the observation space, in our case depth images, which allows us to execute on the robot without full state access. We propose penalized Q cloning, or short PQC. We assume having a planner with full state access that generates plans, in our case collision-free trajectories to the goal. We roll out the planner to generate a labeled dataset of observations, actions, and Q values. Then we clone these to a Q function. PQC combines and improves upon existing cloning methods and has the following characteristics. First, it learns a value function instead of a policy, using supervised targets, similar to accurate. Learning Q values allows fine-tuning using temporal difference learning to improve beyond a suboptimal planner. Second, PQC incorporates a penalty for suboptimal actions, similar to DQFT. This has the advantage that resulting policy imitates the expert better. And finally, we augment the dataset with Q values for all possible actions in each state, not just for the action taken. This has the benefit that Q values of non-expert actions are learned better. We train PQC and all baselines on 500 random scenes with 100 rollouts per scene. Success is defined as reaching the goal without collision or timeout. Costs is a function of distance moved, distance to obstacles, and collision. We train for peg insertion and block stacking tasks. In simulation, we compare the success rates for the block stacking of variations of PQC, ablations, and baselines. For batch PQC, we first generate a dataset by rolling out the expert, then we batch train. For online PQC, we interleave expert rollouts, on-policy rollouts, and training. We do this for all other methods, except for DQN on-policy. On the top right shows the success on the training set over training iterations, and the bottom shows success on a holdout test set. Although the success on the training set is similar to some baselines, PQC outperforms on the test set, which justifies our design choices. The result for the peg insertion task are similar. On the robot, we run proof of concept trials. We evaluate the batch PQC on 5 different scenes, one shown on the right. Their images are transformed by a pix-to-pix scan to appear simulated. The average success rate is about 87%. In conclusion, PQC clones Q values generated by a planner with full state access to a policy that can be executed by the robot. The main design choices are to learn Q-values that can be tuned using TD learning, analyze suboptimal actions, and to learn Q-values for all actions. Finally, we show that PQC outperforms all ablation and baselines on 2 different tasks. Thank you for your interest.
So next talk in this section is learning to plan with point cloud affordances for general purpose textures manipulation.
So in this work, we consider tasks where a bimanual robot must move an object between 2 stable tabletop configurations. And we assume that we are provided with a set of primitive manipulation skills, along with a high-level sequence of the skills that can be used to complete the task. In particular, we utilize primitive skills which take in parameter values and return low-level motions. The parameters are the initial world frame end effector pose and a relative rigid body transformation. All our skills assume that objects are rigid and that the robot will maintain sticking contact with the object. So with these primitives in mind, the problem is then to find an appropriate sequence of intermediate transformations and contact poses so that the low-level motions will bring the object to the overall goal. And the current solution techniques for this type of problem typically assume that the geometry and pose of the object is known. However, the challenging aspect of our setup is the assumption that we do not have access to a 3D model or pose of the manipulated object. So to obtain this plan, while operating directly in the sensor space of the system, we choose to represent objects by a raw segmented point cloud and train neural networks to map point cloud observations to a distribution over the primitive parameters. And because the primitives assume sticking contact, we can directly apply the sampled transformation to the observed point cloud, which enables us to imagine the point cloud observation that would result after executing the skill. So then the transformed point cloud from the first step can be used as the input when we sample parameter values at the next step. And this process can repeat iteratively while checking for feasibility and searching for an overall sequence of transformations that reaches the goal. So for our system, we collect training data and simulation by executing the skills on many differently sized cuboids. And we then train a conditional variational autoencoder, where an encoder learns to map the data to a conditional latent distribution, which is constrained to match some prior. And a decoder is trained to map the point cloud and sampled latents back to reconstruct the parameter values. And then during planning, we sample many values of the latent variable from the prior and use the trained decoder to obtain a corresponding set of candidates for end effector poses and relative transformations. However, when directly sampling relative transformations, it's very possible that the transforms are sampled that are feasible for the robot, but which are unreachable for the object. For instance, the transformation could lead to the imagined point cloud penetrating the table or floating in air or contacting the table in some unstable configuration. So instead of directly sampling transformations, we propose to represent SE3 subgoals with a binary segmentation mask that the neural network must predict, which encodes which points in the point cloud should end up in contact with the table. So we can then use these mask points along with the table point cloud to solve for a transformation that will bring the mask points to be in contact with the table. And our experiments, which are designed to evaluate how well the system can sample its own subgoals and reach them, validate that this choice of SE3 subgoal representation leads to improved performance. We also compare our learned generative models with manually designed baseline samplers in a multi-step planning with cuboids that were not seen during training. And the results show that our learned models provide a large benefit in fixed budget planning success rate. We also have some qualitative results that indicate that we obtain some generalization to different classes of geometry and that the models trained in simulation will successfully transfer to the real world. So in summary, our method enables sequencing primitive skills without requiring a 3D object mesh. And by using primitives parameterized by relative transformations and which assume sticking contact, we enable reliable forward search directly using point clouds. And our results show that this approach offers planning efficiency benefits and has the potential to enable generalization toward multi-step manipulation with more diverse and complex objects.
that's all the 4 talks in this session. Let's see, do we have any question? I do not see any question. So let me ask a question for Thomas first. In your work, right, you should the method is generalized to different class. How do you train your segmentation network so it's generalized to many class? Like what's the training data, for example?
Yeah, that's a good question. So for our work, since we're using depth input, we're invariant to color kind of out of the box, right? So the way we train our network is we are painting the edges and corners of a known cloth, and then using that to supervise the ground truth for depth. Now, when it comes to, so that should take care of color invariance because the depth isn't affected by any of the color. And so as a result, any cloths that say are just varying in color will be fine. When it comes to size, our hypothesis was that because our network was fully convolutional, we would be able to scale to different sizes of cloth. If something looks like an edge within a local patch, then we'd expect it to continue operating in the same way because of our network architecture. And from our generalization demonstrations, we do see that that is more or less true. We are still working on additional generalization experiments to see how far we can push this. But I think those are the two main factors of why our network is able to generalize. When it comes to materials, I think we want to try testing with a wider variety of materials, though we did test with materials as varied as very thick towels and paper, and even that seemed to work pretty well in terms of identifying the edges and corners. But I think it would work better if we had painted towels and materials of varying sizes, of depth sizes, I mean, in terms of materials, for that generalization to work better. So it isn't magic, like we do have some kind of like justifications for why it would work for different color, different sizes, and different thicknesses. Thank you, very nice work. Thanks.
So there's one question from Terry for Anthony. When the experiments are performed on point clouds based on the sensor inputs, how are you dealing with depth noise and occlusion?
Hey, yeah, that's a good question. And at this point in our work, we're not really explicitly doing anything to account for occlusions. The experiments, like the sim to real experiments where we took real point clouds, was mainly tested to see like if the system was going to be still making reasonable predictions on point clouds that came from like a real sense camera that would have some structured sensor noise. Besides that, we're not at this point in time training with any like extra added noise, but I think that it's probably something that could help when we go further with our experiments on real world data. And for occlusions, we have some results that are going to come up soon that are indicating that because of the way that we have our system architected, it's still able to handle occlusions with some reliability, but there's still more work to be done to kind of further evaluate that performance.
Thank you. So let me ask one question for Bernadette. So in your training, you have a discriminator, right? So when you sample this action, you can use the discriminator to tell if the trajectory is realistic or not. Do you also use this discriminator in real task? Because you use it for the training, right? Do you also use the discriminator in the real task?
Hi, yes, thank you for the question. So we do use them for real tasks. So the prediction results that we showed, what we did is we executed tasks on the robot, and we recorded the video data, and then we actually evaluated like the predictive ability of the model using the curious versus random sampling on that task execution, because we thought that if we were evaluating the predicted the predictive ability of the model on like non-tasks, it wouldn't be fair because it would be biased toward either the curious or random sampling if we use the video from either of those policies. But we didn't report completion results because we found that in the data we were getting high variance between the trials, and it wasn't entirely conclusive, and then we couldn't go into lab anymore. So we are hoping to be able to kind of resolve that before reporting the completion results, but we have recorded videos from them completing tasks, and it did seem to be fairly successful. But we were having these variance problems in the randomly collected data as well. So this is something that we were trying to resolve with the prior work that had initially reported it.
Thank you. Kostas also talked about your work this morning.
Oh, yes.
So last question I have for Rick. So how do you're trying to clone the expert Q function, right? How do you train, how do you get the expert value function? Sorry, is the talks also here? Okay, then never mind. Oh, can somebody help? He just raised hand. Guess we need to move right to the panel.
Okay. Can you see me? Hear me? Okay.
Yeah.
All right. So your question is how I get the Q values from an expert.
Right.
So I'm using a planner that that finds a collision fit trajectory in simulation. So in simulation, I have full state access, so I know how to move the gripper with the peg in the environment without causing collision. The planner is also aware of the costs it occurs per time step and for a distance to obstacles. So, and the cost is essentially the sum of rewards that it would receive when executing the trajectory. So in each state, the planner plans the optimal trajectory and also calculates the value by adding up the rewards that it would observe.
I see. Thank you. So for the sake of time, let's end this section.